Have you ever stopped to wonder how your email inbox just knows what's junk? Or how a machine can look at a medical scan and spot something a human eye might miss? Well, it all boils down to a core concept in AI called classification. It's basically how machines learn to sort the world into different buckets, and they're making millions of these choices for us every single day. So let's pull back the curtain and see how they actually do it. You know, a lot of the time, it really just starts with a simple yes or no question. Is this email spam or not? Is that spot on the scan something to worry about, or is it benign? This simple, two-sided choice, this is the bedrock of how machines start to learn to make judgments. And make no mistake, this isn't some abstract theory. This is happening constantly all around us. It's what keeps your inbox clean, it helps doctors make faster diagnoses, and it's the invisible shield that stops a fraudulent charge on your credit card. It's a really simple idea that has a massive impact on our lives. Okay, but here's the tricky part. A machine learning model doesn't really think in terms of yes and no. It just thinks in numbers. So how do we get from some random calculation the model does to a confident decision? We have to translate its output into a probability, a nice clean number between 0, meaning no way, and 1, meaning absolutely for sure. And this is where this really elegant little piece of math comes to the rescue. It's called the sigmoid function. I want you to think of it like a universal translator. It can take any number the model spits out. It could be -5 million, it could be +10 billion, it doesn't matter, and it gently squashes that number so it fits perfectly between 0 and 1. So why is this sigmoid function so perfect for the job? Well, a few reasons. First, its output is always between 0 and 1, so we can treat it like a probability. But the really crucial part, it gives us a clear decision point right in the middle, 0.5. That becomes our line in the sand. And with that line in the sand, the rule becomes incredibly simple. The model does its thing, it uses the sigmoid to get a probability, and then we check it. If that number is 0.5 or higher, the model says, yep, I'm confident enough to call this positive. That's your spam email. If it's anything less than 0.5, it gets labeled negative, not spam. Simple as that. Okay, so that's great for yes or no questions. But, life is usually more complicated than that. What if you're not just sorting spam? What if you're trying to categorize a news article as sports, politics, entertainment, or technology? How do you handle that? Well, we get clever with our strategies. One way is called one versus rest. Imagine you train one model that's an expert on apples. All it does is tell you, apple or not an apple. Then you train another for bananas and one for oranges. When a new piece of fruit comes along, you ask all your experts, and whichever one yells, yes, the loudest, wins. The other way, one versus one, is even more thorough. You train an expert for every single matchup. Apple versus banana, apple versus orange, banana versus orange. They all get a vote, and the fruit with the most votes is our winner. So now that we've got the basic mechanics down, let's apply this to a situation where the stakes are, well, as high as they get. We're going to walk through a hypothetical AI model that's been designed to detect cancer. This is where all the theory crashes into a life-or-death reality. Okay, so here are the results from our model after looking at 100 patients. We have what the model predicted, and we have what the actual diagnosis was. Just take a look at the numbers. At first glance, it looks like it did a pretty solid job, right? It correctly identified 88 healthy people and 7 people who were sick. In fact, if you do the math, you take all the correct predictions and divide by the total number of patients, you get an accuracy of 95%. I mean, that's an A+ score in any test. We should probably just roll this out to hospitals everywhere, right? Well, not so fast. This is exactly where a single number, like accuracy, can be so incredibly misleading. We have to ask a much, much more important question, because that shiny 95% is hiding a really dangerous flaw. To find that flaw, we need a special tool, the confusion matrix. This is brilliant because it shows us that there aren't just 2 outcomes, right and wrong. There are actually 4 ways the model can perform. It can be right in 2 ways, a true positive or a true negative, and it can be wrong in 2 ways, a false positive or a false negative. In our cancer example, one of these errors is infinitely more dangerous than all the others, and that's the false negative. This is when a patient who actually has cancer is told by the machine that they're healthy. This is the mistake that can cost someone their life. So we need better ways to measure performance. Let's start with a metric called precision. Precision basically asks, when the model raised a red flag and predicted cancer, how often was it actually right? This tells you about the quality of its alarms. And when we run the numbers from our table, our model's precision is only 77%. Ho, that is a huge drop from 95%. It means that almost a quarter of the time when it cried wolf, it was a false alarm. But now for the most critical metric for this entire problem, recall. Recall asks the single most important question here. Of all the people who actually had cancer, how many of them did our model successfully find? This isn't about quality, it's about coverage. Did we miss anybody? And here it is, the gut punch. Our model's recall is only 70%. This is the number that was hiding behind that impressive 95% accuracy. This is the aha moment. Let's put that all together. That 95% accurate model we were celebrating a minute ago, it was actually failing to find 30% of the very patients it was built to detect. It sent nearly a third of the sick people home with a false sense of security. This is why looking at accuracy alone can be a catastrophic mistake. Because in the real world, not all errors are created equal, right? A false positive, telling a healthy person they might need more tests, that's scary, it's stressful, it's expensive. But a false negative, telling a sick person they're fine, that can be fatal. In medicine, you will always prefer a model with high recall, even if it means more false alarms. You have to find every single person who might be sick. So, what are the big takeaways from all this? First, never, ever trust accuracy by itself. It can be so misleading. You've always got to look at the confusion matrix to understand the kinds of mistakes being made. Remember, precision is about the quality of the hits, but recall is about the completeness. Did you find them all? And most importantly, the best way to measure an AI? Well, it always depends on the real-world cost of it being wrong. And that really leaves us with one final, crucial thought. As AI gets woven deeper into our lives, making decisions in medicine, finance, even our justice system, we have to keep asking this one critical question. When this machine makes a choice, what is the true cost of it getting it wrong?